Okay, it's witching hour, so I will push the share screen button and see if anybody else joins in as. Okay. Well, that's not right. Okay, hold one. Okay, there we go. I'm Bob Buchheim, as I mentioned, in Gold Canyon, Arizona. And Sean Curry is the co-host here. Sean will be watching for questions and comments in the chat and Q&A boxes, and we'll keep track of that. So after I've gone through this formal presentation, you'll be able to address the questions. And go. I've had an Alpi for 6.5 years now, and my experience is that it's a well-designed, well-crafted instrument for astronomical spectroscopy with small telescopes. What I'd like to do in the next half hour is, number one, help you decide if Alpi is right for you. Number two, describe the equipment, what you need to buy, and how your gear has to work together. And then three, leave plenty of time for questions and discussions on topics that you're interested in. Now, we've all heard that what most astronomers know about the stars, they learned by using spectroscopy. And with Alpi, you can experience that for yourself. Since this is AAVSO, you probably want to make a scientific contribution with your spectroscopic observations, just as you do with photometry, and you can. Shelyak's motto, well, for some reason, how come my clicker doesn't? Okay, technical difficulties here. Let me try this one more time. Okay, that's better. Shelyak's motto is the stars won't look the same, and that's absolutely true.
We're not seeing your screen.
You're not seeing me. Okay, thank you. It's funny, this all worked perfectly a half hour ago.
Okay, we got your screen now.
Okay, so what do the stars look like through an Alpi? Here are some illustrative examples of what you can see. Instead of a little dot of light, the spectrograph enables you to turn your star into a graph of relative intensity versus wavelength. The Alpi spectra range covers the entire optical range from about 3,700 angstroms to about 7,500 angstroms, which means that it pretty well spans the wavelength ranges of your photometric B, V, and R filters. Alpi will show you the features of stellar spectral types, from the hot blue B, O, B, and A stars through the mid-range F and G stars, and the cooler K and M type stars. Stellar classification is usually done with rectified spectra, where you turn the continuum into a flat line normalized to unity. In these rectified Alpi spectra, it's easy to distinguish between the spectral types, A through G through K, and you can see how the spectral features come and go as the effective temperature of the star changes. With the Alpi spectra, you can do a pretty good job of determining the spectral type of an unknown star. From my experience, you can reliably get to within plus or minus 2 or 3 subclasses. So, for example, you could tell the difference between an F0 and an F5 star. But if you have your heart set on doing proper spectral classification, say plus or minus 1 subclass in temperature, and determining the luminosity class, main sequence, giant, etc., and maybe recognizing things like metallicity differences, like Drew Chanowski described earlier this morning. In that case, Alpi is not the answer. And the reason for that is that for luminosity class and the other properties, you're looking for details in the spectral features that require a certain level of fidelity that's expressed by the resolution parameter R. Imagine having two adjacent spectral lines, bringing them closer and closer together. At some point, you can no longer distinguish that they're two lines. Instead, you get a mushy blend, sort of like this pair down here at the bottom. If you call the critical spacing your spectral resolution, delta lambda in angstroms, then the resolution parameter R is defined as lambda divided by delta lambda, the wavelength of interest divided by the spectral resolution. Alpi gives you an R value of about 550. But in order to distinguish luminosity classes, you need a resolution of about 2500. So, and if that's what you're going for, Alpi is not the right tool for you. On the other hand, Alpi's modest resolution means that you can go much fainter than a higher resolution spectrograph can on a comparable telescope with comparable exposure duration. You may have done multicolor photometry on an eclipsing binary star whose color changes during an eclipse. Alpi will show you more detail about what's going on in there, as in this example of BO Mon. The primary is an A-type star. See the bright, sharp bomber lines. It's completely eclipsed by a cooler K-type star at central eclipse, and during that central eclipse, it gets down to about 12th magnitude. The spectra were taken on an 11-inch telescope, so that's an indication of the faintness of targets that you can deal with. Exposure times of 30 to 60 minutes will bring many nova and supernova into range. And the Alpi's resolution is more than sufficient for distinguishing different types of supernova, as Stella mentioned yesterday. With time series photometry, you can watch variable stars change on time scales ranging from one spectrum every few minutes to one spectrum every month or two, depending on the target. Here's a young stellar object, V1117 HER, that you see a series of spectra taken a few nights apart. And you can see the H alpha emission line is changing from night to night. And if you squint your eyes a little and use a little imagination, it looks like the H beta absorption feature is also changing in strength on a nightly basis. Now, on the other hand, if you want to measure binary star radial velocities to support your modeling of eclipsing binaries, Alpi is not the instrument. You'd need a much higher resolution, a much higher R value, something in the 10,000 or higher for that purpose. So you look toward the L high res for that kind of a project. And if you want to watch the evolution of velocity changes in the emission lines of the BE stars or measure accretion disk velocities, Alpi's probably not the right tool. Again, you want higher resolution, but that means that you're limited to brighter targets. You can take spectra of galaxies. Here's NGC 2655 shown on my guider image, and the spectrum of that galaxy. These are really fun to do and interesting, and it's feasible to measure the radial velocity of the galaxy and see the expanding universe. But I think that's more of a gee whiz experience than something that will yield new science knowledge. Planetary Nebula we heard about yesterday. They have spectra that are wildly different from stars. You make spectra of a few of them and you'll never get confused about why a nebula filter works. And there are some really interesting educational projects in the spectra of planetary and diffuse nebula. As for science, as we heard yesterday, planetary nebula can be discovered by amateurs using an instrument like Alpi by surveying point-like objects for characteristic non-stellar spectra. Yesterday also, we were reminded that there's a role for Alpi in the BE star project, which is normally dominated by the high resolution spectrographs. The number of known BE stars falls off rapidly with apparent magnitude, fainter than about magnitude 10. That's almost certainly a selection effect. There's not enough people looking for emission lines in those faint B-type stars, so Alpi could be a great discovery tool there. If you haven't played with spectroscopy before, be forewarned, it's a little different than astroimaging. Remember, when you started doing astroimaging, you learned lessons about the requirements on your telescope, mount, polar alignment, auto-guiding, and spectroscopy comes with all of that and a little more. There's more gear involved. The equipment can be kind of touchy. In addition to images of the target, you must take images that help you do wavelength calibration and also instrumental response compensation, because you're spreading the light of a single star out into a spectrum, a long streak on your image as shown at the bottom of the slide. You tend to need long exposures and excellent auto-guiding. The spectrograph itself has two focal planes, one at the slit and one on the science camera, plus a third focal plane on your guide camera, and they all need to be in focus. And what you see on the spectrum is that streak of light, but what you want to create is a plot of intensity versus wavelength. So you probably need to learn some new software along the way. But you got over the astroimaging humps. Absolutely, you can master spectroscopy with a little effort and a little self-learning. Now, we've seen examples of what Alpi can and can't do. I'll now describe what the Alpi is and how it works, explain the demands that spectroscopy will make on your mount, your telescope, and your cameras, and then we'll have plenty of time for Q&A and discussion. The optical design of Alpi is a classical spectrograph. Starting on the left, the light comes in from your telescope and is focused on the slit. Light that passes through the slit is collimated, goes to a grism, which is a combination of a diffraction grating and a prism that disperses the light. And then the objective lens focuses that rainbow onto the focal plane of your science camera. The slit, the collimator, and the grism are all contained within the Alpi core module. The objective lens is contained within the back module. I don't remember what the name of that is, the rear barrel. And as you can see from the fingers, this is a very compact optical system. The complete Alpi setup includes a calibration module, a guide module, the Alpi core, your science camera, and a guide camera that's not shown in this photo. In the view shown here, the guts of the Alpi, the core of where the grism is located right there in the middle. Here's what the setup looks like on a telescope, plenty of wires. Guide module. What the guide module does is enables you to see what's happening on the focal plane of the telescope. It's an essential part of the system for astronomical spectroscopy. Your telescope has formed an image of the star field here on the slit, which is a reflective optic with a slice taken out of the middle. The telescope forms an image there. The light that is reflected off of that is aimed through a set of relay lenses at your guide camera shown at the top of the slide. So it gives you a real-time view of the telescope focal plane, the stars and the slit. Light that passes through the slit eventually makes its way into the spectrograph and reaches your science camera. The guide module costs about $750, a bit more than the Alpi module itself. Do you need it? Yes. The long answer is, for astronomical spectroscopy, yes, absolutely you need the guide module, and here's why. In addition to the guide module, you may also need a C mount to T thread adapter because the module's camera interface is a C mount, and a lot of the guide cameras, like the one I use, are mounted with T threads. Here's why you need it. Your challenge is to aim your telescope at the target so accurately that the target star falls on the slit, shown here as a little faint red line, white line. That slit is only a few arc seconds wide, so most mounts can't do that. If you tell your telescope to go to the target, chances are that what you're going to see is what's shown on this slide. The target is close, but not on the slit. In this situation, what you see in the science camera is nothing, because there's no star on the slit, hence no starlight reaching the spectrograph. Worse, without the guide module, you have no idea where your target is relative to the slit because you have no way to examine the star field, so you don't know how to adjust your pointing. And sometimes, by random luck, there will be some starlight falling into the slit. But how do you know that it's your target? With the guide module, your guide camera sees the star field and the slit. You adjust your aiming so that the target is right on the slit, start guiding to keep it there, and then what you see on your science camera is this. That's a nice spectrum image, a narrow streak of light running across the science camera. Now, of course, what you want ultimately is a plot of intensity versus wavelength, as we showed earlier, but there's nothing in this image that indicates wavelengths. Any image processing package, Maxim DL or one of the others, will give you a plot of ADUs versus X coordinate along the slit. But in order to translate that from intensity versus X into intensity versus wavelength, you need to figure out the relationship between X coordinate and wavelength, the dispersion equation. And you need to do that quite precisely. That's where the calibration module comes into play. The Cal module contains a neon argon lamp that injects light at precisely known wavelengths. This Cal lamp image, position of those lines in X, and the table of known wavelengths for those lines enables you to calculate the calibration equation, wavelength versus X coordinate. The module also has a little flip shield inside it, so when you turn the Cal lamp on, it blocks the starlight coming in, so there's no need to go cover the telescope aperture. This business is one of the reasons that spectroscopy is a bit more complicated than routine astroimaging. In order to get a spectrum, that graph, you need at least two images: your spectrum image, the streak of the target, and a Cal lamp image from which to calibrate the wavelength versus X coordinate. And it turns out that things are sensitive enough and precise enough that you need a fresh calibration lamp image to go with each target set of images. Like any other astroimaging project, you'll also need darks and flats to remove image artifacts. Darks are handled in the normal way. At the end of the night or the beginning of the night, you cover your scope or close the shutter, take a set of images with no light hitting the camera. Flats are a little trickier. You want to inject a uniform illumination into the slit, determine the pixel to pixel sensitivity variations, deal with dust motes on the slit of the spectrograph, and the overall sensitivity of camera and response function versus wavelength. The Alpy Cal module includes a tungsten lamp that gives you a nice flat image through the slit. The Cal module is really convenient to use. You aim your telescope at the target, take your target spectrum images, flip a switch to turn on the calibration lamp, and you make your wavelength calibration image. Simple. But it costs about 650 bucks. If you want to save some money, and if you're a skilled tinkerer, there are other solutions that work just fine. In the top photo, the operator is holding a Philly lamp. in front of the telescope aperture, Phillies are a decorative lamp that emits argon spectral lines, and you can use that for wavelength calibration. And the bottom image, an incandescent lamp illuminating a diffuser in front of the telescope creates a nice flat image. These are perfectly good solutions, but I think many people will find that the Cal module's convenience is worth the price. It has two other nice features. First, it was designed with automation in mind. In addition to manual switches to turn the lamps on and off, the module can accept commands from Sheliak's Spock's box or from a homebrew electronic module, making it compatible with simple automation. Second, there are in the community now quite a few users who know what the calibration module image should look like and how that image is used. That'll make it easier for them to help you if you run into calibration questions as you make your way up the road of spectroscopy. Now, I've mentioned pointing. Here's a picture of the Alpi, this time shown on a C11 with the Celestron fork mount. You can see the calibration module, the guide module, the Alpi core, and the science camera. And again, the guide camera is just barely sticking out the back of the guide module. The Alpi is lightweight, 4 pounds, 5, depending on what camera you're using. So that should be no problem for most telescopes and mounts. But it's long. The dimension from the calibration module to the back of the science camera here is about 7 inches, not including the focuser on the telescope. And no big deal with a German equatorial mount, but with a fork mount like this, that can severely restrict the range of declinations that you can point to. In this photo on my fork mounted C11, I had to add a star diagonal to bend the optical path so that I could point at VV Cepheid, declination about 63 degrees. And I barely got there. I had about a ½ inch before the Alpi was going to bump into the base of the fork mount. So beware of that if you're on a fork mount. The guider field of view obviously depends on the focal length of your scope and the size of your guide camera chip, but think in terms of about 10 arc minutes of total field. It's pretty small. So you'll need good pointing to put the target into that field. And with such a small field, you may not be able to do a plate solve on the image. I always use just eyeball matching of the few stars in the image to a star chart to identify the target, and then manually move it over to get it on the slit. That narrow field for the guider is not an issue that's unique to Alpi. Virtually all spectrographs face this challenge. Because the starlight is spread out into a pretty long streak, the exposures will be much longer than you're used to in CCD photometry. You'll always need to auto guide because you need to keep the star in that slit that again is only a few arc seconds wide. As in astroimaging, it's standard practice to make sub-exposures of 5 or 10 minutes, depending on how your mount tracks, and then sum them during post-processing to achieve the equivalent of an hour-long exposure. Earlier, I showed spectra of that young stellar object V1117 HER. That was about an hour and a half of total exposure in each of those spectra, 9 subs of 10 minutes each in that case. Most of you have probably been through the concept of matching your telescope to your camera for photometry. Remember, you consider the seeing, the aperture and focal length of the scope, and the pixel size of the camera, and your goal is to get well-sampled star images, say 3 or 4 pixels across the full width half max of the point spread function. There are similar concepts in spectroscopy, and they show up in 2 places. First is getting most of the light from the telescope to go through the slit. And then second, getting a well-sampled image of the rainbow on your science camera. We'll deal with the science camera in a few minutes. But first, take a look at the situation getting the light from the telescope through the slit. Here's a close-up view of the slit in your spectrograph, and consider what the star image looks like. If the star is a big blob, bad seeing, or a long focal length instrument, then only a small fraction of the starlight gets through the slit. If the target's bright, that's not a big deal. But if the target is faint, if you're only getting, say, 20% of the light into the slit, then you're going to need 5 times as long as an exposure as you would have if you get all the starlight in. And that can be a problem, especially as you move to fainter targets. The ideal situation is that the star's point spread function is nicely matched to the width of the slit. Most of the light gets in, but the illumination across the slit is still reasonably smooth. In the bottom situation here, the star image is tinier than the slit, so it can kind of rattle around inside the slit. You still get 100% of the starlight through. That's good. But there are a few effects that can argue against having the star image be much smaller than the slit width. In most situations with the typical backyard seeing, we may not have to deal with that. But in any case, that means that you want to do some calculations to find out how well your telescope and the Alpy's slit will play together. Alpy's standard slit is 23 microns wide. Now let's assume that the size of the star image is driven by the seeing, which is the case for most of us. 2 to 4 arc seconds is typical in my backyard, and I think probably for most of us. This equation will tell you the size of the star image. The seeing in arc seconds times the focal length of the telescope in millimeters divided by 206 gives you the size of the star full width half max in microns. So for example, 3 arc second seeing, an 8-inch f10 telescope leads to about a 30 micron star image. That's a good match to Alpy's 23 micron slit. Indeed, Alpy was designed with telescopes like that in mind. You might want to use a focal reducer. I did on that C11. Turned it into a f6.3 instrument. Same 3 arc second seeing. Imagine an 8-inch f6.3. And now the star image is 19 microns. That's just about a perfect match to the 23 micron slit. So go ahead and use the focal reducer, but there's a limit to how far you can go. Alpy's internal optics can only accept light cones as fast as f4, and I think Shellyak recommends f5 or slower in order to not get into internal optical problems. Now, you're going to want to collect a lot of starlight because of the way you're going to be spreading the spectrum out on the camera, and normally you think of, I need more starlight, you're tempted to look toward your largest telescope. Turns out that might or might not be the right direction, and the trade-off is kind of tricky. Larger telescope brings in more light, but it probably has a longer focal length, so the star point spread function at the slit has gotten larger, so a smaller fraction of the starlight makes it through the slit. So it isn't obvious whether the combination of more light coming in and a smaller fraction getting through the slit is a net winner or loser. The thing to do is play with this equation using the parameters of your own telescopes and decide which one to put the Alpy on. There are situations where the smaller scope may be the better choice. Now, at the other end of the spectrograph is your science camera. It's the one that takes a picture of the streak of a star or the rainbow spectrum of an extended object. Some important things to consider. First, the back focus of Alpy is pretty small. I think it was designed around the ATIC cameras, and they work nicely. If you're going to use a camera that you already own, check the spec sheet and confirm that your camera and Alpy will reach focus together. Talk with the Shellyak team if you have any concerns on this subject. They'll help guide you whether there's a problem or not. Now, back to matching cameras and point spread functions. You remember again for photometry, you knew that you want the pixel scale and the size of the star image to be such that the star image is well sampled, 3 or 4 pixels across the full width half max of the point spread function. There's a similar situation for your science camera looking at the spectrum, but the science camera is not looking at the star. It's looking at an image of the slit. This is an essential optical concept, but it can really make your head hurt while you're getting used to it. So look at this simplified diagram of Alpi. You've got a slit, collimator, grating, camera or objective lens, and then the rainbow on your science camera. Ignore for a moment the grating. What you have is a relay optics that takes the slit and makes an image of it down on the camera focal plane. That's why people say that the spectrum is an image of the slit. Now, suppose, obviously, if you have white light coming in, you get the complete rainbow on your science camera, and it's as tall as the slit is tall. But now, suppose instead of white light, we illuminate the slit with just a single wavelength. Then that one wavelength is the only thing that remains in the spectrum, and there it is. Now again, that's an image of the slit. It is not infinitesimally narrow. The Alpy's optics are approximately a 1-to-1 relay, so the width of the slit is 23 microns. The width of that image is also 23 microns. To be well sampled, you want probably 2 or 3 pixels across the width of the slit image. That slit represents the smallest resolvable feature in the spectrum. So you want 3 or 4 pixels across it to divide that into 23 microns. Somewhere in the 6 to 8 microns per pixel on your science camera is about the right place to be. For the guide camera, the relay optics are also 1-to-1, so the same kind of resolution requirement applies. There are plenty of softwares for auto guiding. Any one of them will work. If you haven't already, take a look at PhD2 Guide, freeware, and it has some really neat special features for guiding a spectrograph. So, personal opinion, if you're going to buy the Alpi, buy it with the guide module and the Cal module, and it'll do everything you need for education and research projects in astronomical spectroscopy. Because of the compact and symmetrical design, it is very mechanically and thermally stable, and that is worth emphasizing. Most spectrographs are subject to some calibration shift as the telescope points and tracks. Here's the back of your telescope and the Alpi sticking out of the focuser. Gravity is pointing that way, and that puts strain on the optical path. The image is obviously not to scale, but it happens. The tug of gravity will bend things and change the position of images and wavelengths a little bit on the science camera. And then when you flip the telescope and look in a different direction, the gravity vector is now acting in a different way on the spectrograph, and so things shift. Now, Alpi, because of its compact and symmetrical design, is almost immune to that. When I swing from one side of the sky to the other, the shift is only a few microns, which sounds tiny, but that's almost 1 full pixel on the science camera, which is 3 or 4 angstroms of wavelength shift in the spectrum. And you can see a shift of that magnitude in your Alpi spectrum. So that's why you always take a new calibration lamp image with every target that you're pointing at to eliminate the effect of that gravity strain. Most spectrographs are also sensitive to the thermal environment. Changes in ambient temperature cause focus shifts within the spectrograph optics. Alpi, as far as I can tell, is immune to that over reasonable temperature swings. If your science goals can be accomplished by a low resolution spectra, an R value of 500 to 600, and particularly if you want to deal with faint objects, Alpi is an outstanding instrument. You can reach magnitude 12, 13, 14 without too much trouble, long exposures obviously, and it's relatively simple to use. So I'm right on schedule, and we have time for questions and discussion. I'm going to try high technology with Zoom here. And as a way of deciding what to spend the next 20 minutes on, if you all can see the poll and vote for the one or two or three topics that you'd like to talk about. Sean, is that actually showing up?
Yes, I see it. It
Okay.
looks like I can't vote, I guess.
Oh, yeah. Okay, somebody's voting, so we're we're getting answers.
By the way, first of all, thanks, Bob. That was really good. And I'd like to reiterate what Bob said, that the Alpi is a great instrument. I've been using it for about a year. And I'll say one thing, it's working great for me now, but I sure wish I'd had this presentation when I started a year ago. So hopefully if any of you are just getting going or thinking about an Alpi, refer back to this because you'll find the advice here will help you a lot.
Okay, I'll put the recording on Amazon for the right price.
And by the way, we believe all of these presentations will be available later. I'm not sure if they'll be on the YouTube channel or on AAVSO website, but
yeah, I think they'll end up freely available on YouTube sometime after the annual meeting is complete. Okay, there seems to be a consensus building around processing steps, adjustments during the imaging sequence, and how do I assemble and align out of the box?
and we do have a few questions in the Q&A as well, Bob.
You want to relay those while people are voting?
Yeah, let's do that. The first one from Rick asks, relating to sub-exposures, you said sum them. Do you mean that, or do you mean median or averaging of the subs?
The software that I use is ISIS. And I don't remember whether it's sums
I think
or
it
averages.
sums because the ADU counts get really large. I think it just sums them, doesn't it?
Yeah, and of course mathematically, once you're working in 64-bit arithmetic, there's really no difference between summing and averaging. Median, as you know from your astroimaging, is a great way to get rid of cosmic rays and single image artifacts. So if you're subject to that problem, there's nothing wrong with median combining. ISIS has a cosmic ray eliminator that seems to work pretty well.
Rick also asked, can you make any recommendations for cameras, particularly within the ZWO line? Color versus mono, sensor size, cooling necessary?
Definitely mono, and probably cooling, although I gather some of the CMOS, I don't know about CMOS. I'm using an ATIC 314 CCD. So I know the ATICs work. I think the ZWOs also are have nice short back focus to mate to the Alpi. When I was buying mine, I talked with one of the people at Shellyak about using my venerable old ST8 And they said, yeah, we can sell you a relay optics assembly, but frankly, we recommend against it.
The next question is, I'm way over sampling with 2.4 micron pixels. Do you recommend binning 2x2? It's a CMOS camera.
Yeah, that's, I've heard arguments on both sides about whether you should bin on the chip with a CMOS, or let the larger image size go and do your binning in post-processing.
Here's a question from, I think, a familiar name. It looks like it might be John Wetmore, asking, Bob, do you think the UVEX will be replacing the Alpi and the Lisa?
Interesting question. Certainly it will have all the capability of an Alpi. I don't remember how the prices differ. I think since you still have to buy if you already have an Alpi, you can take your guide module and your calibration module and apply it to UVEX. I don't know. That'll be an interesting decision to have to make. If you're starting all over, you probably ought to look hard at the UVEX.
Here's a good question. Can you talk a bit more about back focus? If my scope has a back focus of, say, 55 millimeters, do I locate the slit at that point, or that point minus the distance from the front of the camera to the chip?
Yeah, good question. Let me see if I can open up. Are those slides showing?
Yes.
Okay, let's go back. Okay, this is not bad. The slit is the focal plane of the telescope. So, and it's, you know, maybe 1.5 inches from the front face of the calibration module. So your telescope needs to reach focus on the slit. Normally, I think that's not much of a problem. The back focus issue is the camera lens that's hidden within the rear barrel of Alpi, and the focal plane, that's where the focal plane of your science camera needs to go. That is about 1/2 inch. I think it's 13 millimeters or thereabouts. It's really small. And that's the back focus challenge for your science camera.
And that, as Bob has said, that's definitely the thing you want to check before you buy a camera, is whether that back focus will work.
I hope that answered the question. I hope it was the right answer to the right question.
But as you said, Bob, I think getting the focus of the telescope on the slit is usually not a problem. You might even have to put an extender or something in there, but it's the science camera back focus that's the critical one.
Yeah, I moved to an RC about 1 year ago, and previously using a Schmidt Cass. You know, and one of the things that you get really used to with a Schmidt Cass is you can focus anything. You've got virtually infinite back focus with the RC and a fixed focal plane. Yeah, I have spacers that I need to put in to bring everything into focus.
The next question, this is a good one. How is mechanical robustness for those that set up and tear down each observing session?
Alpi is surprisingly robust. When I moved from Southern California to Arizona, I took the Alpi off the telescope, put it in a foam lined shipping container. The moving van took it to Arizona. It sat in the garage for almost 1 year while the observatory was being built. And I put it on the telescope and I made no adjustments, and it was still working very nicely. Later on, I did a little touch up on the focus, but I'm not sure that I really needed to. It's pretty solid.
The next question is from Richard. How do you set up PhD2 to work with the guiding module?
Your guide camera, good point. Your guide camera is a guide camera like any other, and I can get to an image here. I think so this is what the guide camera sees. Your target on the slit, and maybe some other stars around. Do the thing you normally do with any guiding software. Train it, the gains, arc seconds per step in X and Y, and then either click on the target on the slit as the guide star and start guiding, or particularly if the target in the slit is so faint that it kind of disappears, you can do an offset guide and use some field star. One of the neat things about PhD2 is it will inject a synthetic slit. It'll put a little reticle where your slit is, so that you'll know when your target star falls into the slit. And also it can remember the lock position. So when you move to another target and you get that first image where it's not quite on the slit, you click on the star, say this is my target, tell it to move that to the lock position in memory, and it'll move it right onto the slit.
Gary notes that to do with the question of whether the UVEX will replace the Alpy and so on, is the UVEX currently looks to be about 3,800 euros, and the Alpy is about 700 euros. So that's 3,800 plus you need the guide module and the calibration module. So
yeah, so that might help make your decisions at some point. Yeah. Although, I mean, the UVEX really is a beautiful idea.
Yeah. Conrad asks, how do you focus the camera with that back lens?
Good question. I think, let's see, there's a picture here there. This is the interface between the Alpi and the science camera. And you can see these knurled knobs here. There's 6 of them, 3 in a circle and then 3 in the next circle. You loosen those up, and it's sort of like a helical focuser. You turn a little knob, a fraction of a turn, and then lock it down and take another image. So it's a meticulous process, but it's very precise, as helical focusers are. And you'll probably only need to do that once, and you do it on the bench as shown here, not on the telescope.
And I think I'll reiterate that advice when you're setting this up the first time. Do it indoors on your desk or your bench, and do all that focusing ahead of time.
And it looks like that question of assembly got a fair number of hits on our poll. I think there are some images that, okay, yeah, here's the deal on when you get the Alpi out of the box, read the manual. It is a very well done step-by-step. How do you put the pieces together and how do you check them? 95% of the assembly process is done on a bench in your kitchen or somewhere like that. Do not jump right to the telescope. I've talked to a few people that got overly excited, went to the telescope, and then got frustrated. You do all the assembly on a tabletop. Go very methodically, very step by step. Things like that focus question. You're going to put it together, take an image. You're going to say, "Oh, it's out of focus." Turn the focus a little bit. Write down in your notebook, "I moved it counterclockwise by 1/4 turn." Put it together and see the image again. If the image is improved, take it apart, move it another 1/4 turn, write down in your notebook what you did, so that when you're iterating, you'll be able to reconstruct the crime. So that's my advice.
The next question is, your skies seem pretty dark. How well does the sky background subtraction work if you're imaging faint targets under, bright city skies?
Good question. It works great. If you remember the procedure, you've got a streak of light as the spectrum of a star on your image, and you put in your processing, you'll put a narrow horizontal line across that and process within that in some optimal fashion to extract ADUs versus exposition. You're going to turn that into signal versus wavelength. Above and below that, there's no starlight, but there is skylight. And so you pick a box above and a box below, do the appropriate averaging, and subtract that from what's in your measuring aperture on the spectrum. So the measuring aperture contains star plus sky. You subtract sky just kind of as you do in photometry. And it works very well. As I mentioned, I use the ISIS software, but other softwares use essentially the same procedure, and it's very reliable.
Philip asks, will the slides be distributed like the ones from the first day? And I believe that's true. The presentation itself will be available. Is that right, Bob?
I don't know. I gave it to Lindsay, and I don't know. I have no problem sharing them.
But this video of this presentation itself will be.
Yeah, it should be.
Here's a good question. Is the bright donut artifact in the guide view normal?
Yeah, I have a slide on that. The answer is yeah. Let me see here. If I share screen, somewhere in here. Yeah, you can. It's perfectly normal. And okay, are you seeing that?
Yeah.
Okay, so that's what you're talking about. Here's the if I slideshow. So you see the target and you see the donut. It's a perfectly normal artifact. Where it comes from is, you remember the light's coming in from the telescope, passing through the slit.
Oh.
The slit is reflective, and so what reflects off is going off to the guide camera. But what that coating is coated onto a glass slide. And so when you hit that front surface of the glass slide, 4% of the light bounces off. It's out of focus and it's not in the right position. That's what causes that ghost image. The critical thing is it does not make its way into the spectrograph. So it's only an artifact you see in your guide camera.
Next question is another good one. How often do you need to refocus during imaging on an object, and is an electronic focuser mandatory?
I don't know about mandatory, but it's a really good thing to have. Let's no, shoot, I did something wrong here. Do I need to refocus during an imaging run depends very much on your telescope and the situation, because you're keeping a focus on the telescope on the slit. That's a function of your telescope and your environment. The focus of the science camera on the back of Alpi, I have never seen a situation where I needed to refocus that. Even here in Phoenix, where, in the summertime, it's 100 degrees at midnight, and in the wintertime, it's 30 degrees at midnight. I've never seen a problem there. Depending on your telescope, with my Schmidt-Cass, there was a pretty pronounced thermal shift. And so in the course of the night, I'd have to keep refocusing on the telescope on the slit. And you do that by looking through, looking at your image on the guide camera.
Jim asks, how much back focus does the calibration module and guide module use?
They're about, I don't know, about 1 inch each. So, you know, a couple of inches. Let me, here, I just happen to have it. So yeah, here you are. That's the cal module. This is the guide module, and the slit is kind of halfway down the guide module. So 1.5 inches, 2 inches tops.
Rick asks, what can the Alpi do that the star analyzer can't do?
What, you know, the star analyzer resolution is something that you can adjust all over the place, depending on how many spacers you put between the grating and your focal plane. I think we saw that during one of the talks yesterday. On the other hand, the limitation on the star analyzer is the resolution is set by the star image. You know, if you got bad seeing that night, so the star image is bloated, the spectrum resolution is the size of the star image. The advantage of a slit spectrograph is the resolution is set by the slit. And that's why, for example, Francois talked about on the UVEX, you can use a larger slit, but that will reduce your resolution.
Bob, we're down to the last couple of minutes here. Is there anything out of the poll that you'd like to talk about briefly?
Well, you know, it looks like we may have, well, we haven't talked about processing steps.
Yeah.
And I can, oh boy, spectral processing in 2 minutes. That'll be interesting. Let's just try this. This is more concept than anything else. The first part of the processing step is taking your calibration lamp image and figuring out the dispersion equation. How many, you know, at X coordinate, what is the wavelength? That's for Alpi important because that's a very nonlinear relationship. The dispersion is not constant. Once you've done that, you can now draw ADUs versus wavelength, but you've still got to deal with the light that came from the star had to pass through our atmosphere, which has absorption and scattering that is a very strong function of wavelength. And then you've got the response of your instrument, the transmission of the slit, the transmission or efficiency of the grating, and the response of the camera. All of that distorts the continuum shape in your spectrum. And so in these low resolution spectra, you want to compensate for all that so that you can ultimately get a graph of intensity versus wavelength that represents the exo-atmospheric, outside the Earth's atmosphere, relative flux from the target. So that's what you're trying to do. The steps, let me see it. I have, do your calibration, measure a reference star of known spectrum. Miles catalog is kind of the go-to place for that. Do your sky subtraction, get a relative intensity of your target, you know, versus wavelength. And then your software will decide how you handle the target region on the image, how do you optimally sample and collect the light there? How do you remove the sky? How do you deal with image distortions? You may have noticed on the calibration lamp image in Alpy, the lamp lines are a little curved. That's colloquially referred to as smile. That has to be dealt with. ISIS does a great job. Shelyak's new software, Demetra. Sean's have experience with that, and I think it's panning out very well, right, Sean?
Yeah, and I think for getting started, especially, it's a really good place to start, and it's freely available. You can download it now and practice with it. So.
And it kind of forces you to go through all those correct steps. It sounds complicated. It does take you a little effort to learn, but it's not that painful. I think we're supposed to stop now. In fact, I'm a little surprised we haven't been kicked out. We're 2 minutes over. Hey, everybody, thank you very much for joining us. I hope this was entertaining and useful. Most of you know how to get a hold of me, OCA_Bob@yahoo.com. If you have any further questions, or look me up as BHU on AAVSO and send me a note. Thank you all very much. Thank you, Sean, for pulling this off.
Thank you. Very, very helpful information.
And you all have a good time at the next breakout session.
Thank you, Bob.
Thank you. Bye-bye.
Bye.